We're going to go ahead and take a look at numeric integration. Now, with numeric integration, basically you're coming across some functions that you can't integrate. Either you don't know how to up to this point, or there is no antiderivative that really exists. Now, a lot of times when you're dealing with polynomials, trig functions, exponentials, and logarithmics, we can go ahead and get some of these functions to integrate, but some of them can't be. Well, here's a relatively basic function that you might be coming across, but there is no antiderivative of this that exists. So if we had a definite integral, how would we go about evaluating that? Well, one of them is kind of what we were doing beginning of the course, where we did left endpoint rectangles, right endpoint rectangles, and trapezoids, and you could increase the number of intervals so you could still get a fairly accurate answer. Instead of doing left or right endpoint rectangles, there's also midpoint rectangles where the middle of the rectangle touches your curve, and then we're going to also look at Simpson's rule. All these are ways to be able to go ahead and approximate that area. Now, with Simpson's rule, sometimes called the tangent line approximation, you go 1/3 times the change in your x, which is the width of your interval, and then you go your first height plus 4 times your next height plus 2 times the following height plus 4 times the next height plus 2 times the next height, and so on until you get to your last height, and that's just your normal last height, just like your normal first height, and you weren't multiplying by anything. Now, Simpson's rule works if you're dealing with an even number of divisions. So it would work if you had 10 divisions or 28 divisions. It would not work if you had 27 divisions because it's an odd number. Now, Simpson's rule can also be figured out by using m, which is your midpoint, so doubling m, plus t, which is your trapezoid approximations, and then going 1/3 of that. So if you double your midpoint and add your trapezoid and do 1/3 of it, you get the exact same thing as you do from this formula here. So sometimes if you know your midpoint and trapezoid, you can just use this versus the whole thing. And then there's your trapezoid. There's a couple ways you can look at your trapezoid. You could say it's half the first height plus all your other heights plus half the last height, if I can talk here, all multiplied by the width. Or you could say it's the first height plus do you double all the other heights plus the last height and then all multiplied by half the width. Now the reason you're doubling some of these heights, you just have your first height here, but this next height is used in 2 trapezoids. So that's why we end up having to double it. This one's used in 2 trapezoids for your height, the one on the left and the one on the right. But your last height is only used in 1, so we're not having to double it. So at this point, let's go ahead and take this. And by the way, if you go to our course website, there's a program there that you can type in. Now, beginning of the course, we did a program for these first 3. However, if you use the program that's on our course website, you'll also get the midpoint one and Simpson's rule that it will spit out. So you might want to consider doing that. Now, here we want to find the area underneath our curve of sine x over x. And we want to do 10 divisions. So that means we could do Simpson's rule if we want. Now, since we're given a function here, I'm going to go ahead and put this into my y equals on my calculator. I'd want to make sure I was in the radian mode. But for the most part, on a problem like this, we got to kind of fool our calculator. Because if you did plug in 0 on top and 0 on the bottom, you get 0 over 0, and your calculator is going to say, I can't do that. So basically, instead of starting at 0, we just try something really close to 0, but not technically 0. So it's still going to give us a very accurate answer. So for your beginning, we could put this in. Your end, you could put in 1, the number of pieces we'd put in as 10, and you use your calculator program either from beginning of the course, which would give you these 3, but I would encourage you to go to our course website and type in the new program, and that will give you then all 5 of these. And then you will get this. Now, if you wanted, instead of using Simpson's rule from the program, you could just take your trapezoid, take your midpoint, and double the midpoint, add your trapezoid, and do a half, and that would also give you Simpson's rule. Now, numeric integration is sometimes nice when you're dealing with data rather than a function. If you're given a function, you can always put it in the y equals on your calculator and use your program that way. But here we are asked to do the trapezoid in Simpson's rule based on some data, in which we're looking at trying to estimate the distance traveled. And all we have at this point is velocity versus time. Our time is here, our velocity is here, so the initial time we had a velocity of 12. After 1 hour, we had a velocity of 14. After 2 hours, we had a velocity of 17. So if you plot all these points, you get this graph over here. Well, you should remember that the area underneath your velocity graph is your distance, and that's what we're looking for. So we could go ahead and use Simpson's rule and the trapezoid rule. Notice I'm using 1/2 your height, which is your change in your interval, plus or times your first height plus double all your last or other heights plus your last height. Now, when we're looking at your delta x, that's what you're going up by each time here. And in this case, we're always going up by 1. Going up by 1, going up by 1. So your delta x right here in front is 1. Your first height would be for your 12, so that's x sub 0. And then you got to double all your other heights. So you're going to go and have to double your 14, double your 17, double your 21, and keep doing that, doubling all your heights, except remember your last height you don't include in the doubling, you just take it as is. And then I would go ahead and type this into my calculator all in one line, and we would get approximately 160.5 miles. That would be a pretty good approximation. We could also go ahead and use Simpson's rule here. For Simpson's rule, it's 1/3 what you're going up by each time. And once again, we were going up by 1 unit each time for your change in your x. Then you have to go your first height, which once again is 12. So then we have to go plus 4 times your next height, so that's 4 times your 14, plus 2 times the next height, so that's 2 times the 17, plus you repeat going 4 times your next height, plus 2 times your next height, plus 4 times the next height, and you keep doing that, except your last one, which would be our 17, you don't do anything to. It's not doubled, it's multiplied by 4. So then I would go ahead and type this all in one line, and in that case you would get 161 miles. Both of these would be a good numeric approximation. And here we have a blizzard occurring with a snowman in the middle of the blizzard throwing snowballs at an albino deer.